Okay, I'm Dan Gohman. I'm going to be talking about the LLVM Code Generator. This is the back end of the compiler as opposed to the front end that Steve was talking about.
Can you be a little louder, please?
Okay.
Thank you.
So the first question I'm going to answer is, what does the CodeGen do? What is a CodeGen?
Louder.
Okay. CodeGen, from an LLVM IR perspective, is essentially a very large analysis. It reads LLVM IR, and it produces machine code as output. The goal is to produce as efficient as possible machine code for some definition of efficient, and also to run as quickly as possible for use in very fast compiles as well as JIT compilation. The LLVM Code Generator has a bunch of different responsibilities, and you can place them into more or less 4 main categories. There's the preparation phase. This is actually consists of a couple of LLVM IR transformations that operate on the LLVM IR directly. So in some senses, they're not part of CodeGen technically, but they are part of the LLC tool, so I'm mentioning them here. They do some simple transformations that help out the later phases of CodeGen. The next main category of things that happen in CodeGen is the SelectionDAG phase. That's what I'm going to be spending most of my time talking about today. This phase does instruction selection as well as the scheduling. After the SelectionDAG phase comes the registry allocation phase, and Evan's going to be talking more about that after this. And then finally, output, either to LLVM IR, or assembler source or machine instructions in memory ready to be executed currently. So looking at the SelectionDAG phase, which is where I'm going to be spending most of my time, the input is LLVM IR, and I'm going to walk through an example of this LLVM IR code. This is a simple loop. It does some simple operations that I've selected because they have some interesting properties in CodeGen. So the main data structure is the SelectionDAG. You can see the graph on the right or the left here. I don't expect you to be able to read that, but this is just mainly a bit of detail, and I'm going to be zooming in for various parts to show some detail. So the main node in the SelectionDAG is the SD node. Nodes can have multiple operands, and in the CodeGen, those are called SD uses. And unlike LLVM IR, in the SelectionDAG, nodes can have multiple values, multiple result values, and we call those SD values. This node has only one. Okay, I'm sorry.
Talk slower and louder.
The SelectionDAG is a dependency graph. The black arrows that you can see in the graph are data dependencies. The blue dashed edges are chain dependencies. Chain dependencies is SelectionDAG lingo for control and sequencing. So when we have a load that must follow a store, we have a chain dependency that indicates that, for example, this load over there and the store over there must be sequenced. At the top of the graph is an entry token, which is essentially the token that indicates the very beginning of the block. And in the middle of the graph, we also have a special node called the token factor, which is a way of having multiple chain edges be combined into one so that it can be conveniently depended on by another node. The LLVM SelectionDAG is somewhat unique among compilers in that we use the SelectionDAG. There's no sequence of instructions at this point. In order to get from this form into machine instructions, we have to do scheduling. There's no option to avoid scheduling because all we have here is a graph with no order. The SelectionDAG does automatic CSE, so when you create a node, it will check to see if there's already another node with the same operands and the same opcode, and it will reuse that node instead of creating a duplicate node. The SelectionDAG is lower level than LLVM IR. We're going down to machine code progressively lower and lower. And all the graphs that I'm going to be showing you today are graphs that are produced directly from GraphViz. And these are the graphs that we use when we're working on this. So this is what we see when we're working on CodeGen. It's very much these pictures. The SelectionDAG has 6 main steps. The lower step, which is producing the SelectionDAG, looking at the LLVM IR as input, and writing a SelectionDAG as output. The combine phase, which is a p-pool style optimizations and simplifications. Legalize, which lowers operations that are not legal for the machine. Another pass of the combine phase to do more optimizations. Then we do instruction selection proper, and then finally scheduling. So I'm going to walk through each of these steps in detail. The first step is the lower phase. And here we're taking our LLVM IR on the left and translating into our SelectionDAG on the right. And I'm just going to highlight a few key pieces here. We have an add. This turns into an add node in the SelectionDAG. One of the things to note here is that our SelectionDAG is only looking at one basic block at a time. So in order to have values that are live across more than one basic block, we actually use virtual registers. And we have a special copy from reg node to indicate that this add is using a fee value. It's using a value that's potentially coming in from outside the block. So we use a virtual register to represent that. Here I'm showing a load. Loads are lowered into a fairly straightforward load nodes. Note that the load node has both a chain input and a chain output for dependencies that the load has and for other things that depend on the load. And then finally, I'm showing there's a conditional branch. This is a loop. And this gets lowered into a conditional branch in the LLVM IR. At the bottom of the graph, we have the graph root, which is basically a special node indicating that this is the bottom of the graph. And it also happens that we created a constant 0 somewhere along the way. We make a trade-off in constructing the graph. Right now, we opt for simplicity over the optimizations right away. We have the build phase, the lower phase, is aiming to be as correct as possible, and right now as simple as possible. And we leave it to the combine phase to optimize things like this away. So I've highlighted a few things that the combine phase is doing for us in this graph. In this conditional branch, it turned out that when we created the condition, and then when we created the branch, we decided that the condition was going the wrong way. We wanted to invert the condition. Well, the build phase just created a simple XOR by 1 to invert the Boolean condition. And the combine phase recognizes that, and it'll actually reverse the condition and simplify that to a simple branch. The combine phase is also responsible for canonicalizing the graph. So it'll turn this multiply into a shift. The next phase is the legalize phase. In SelectionDAG speak, legal refers to an operation or a type that can be directly represented on a machine. So this is a type that will fit exactly into one machine register, or an operation that can be done as a single or a small set of machine instructions. So I've shown, this is a 64-bit add, and right now in my example here, I'm doing compilation for x86-32, which does not have a 64-bit add instruction. So legalize is responsible for splitting this into two 32-bit adds, and for using the condition codes of the x86 to handle the carry bit. We have two special nodes, add with carry and add extended, and a special edge type indicating that we're using a condition code edge here. This is one of the ways in which the SelectionDAG is lower level than the LLVM IR, that we actually explicitly represent these things directly. Here's a 64-bit multiply, same story, except multiply is a little bit more complicated. In particular, it involves a node that has multiple result values, and I just wanted to show that. Legalize is heavily parameterized by individual target nodes. And in addition to targets being able to specify custom behavior, they can actually have custom nodes. So here we have a conditional branch being legalized for x86 using a special x86 specific node type. And targets can define any number of their own node types to aid in legalization. After legalization, we actually run the combine phase again because there's often more opportunities for optimization. One of the things that happened here, we were multiplying, our 64-bit multiply was being multiplied by the constant 101. That means that the high part of the multiply ended up multiplying by 0. That's obviously something we can simplify. I'm also going to point out that the combine is an iterative path, so it'll notice after simplifying the multiply to 0, that result was added. So we can simplify that whole 0 multiply add chain down to a single 0. Now that the graph has been legalized and simplified and canonicalized, now we're actually going into instruction selection proper. This is sometimes called DAG to DAG instruction selection in the source for historical reasons. So I'm going to show a few examples of instruction selection in action. This is the add that does the loop control variable, is just adding a variable by 1. We're compiling for x86, so we select this to an INC instruction, inc. At this point, this opcode corresponds directly with an x86 machine opcode. And the R on the end of that opcode means that the operand is hopefully going to be in a register. If we end up spilling the register, it could end up turning into an M. But for now, we're going to say everything is going to be in a register. The instruction selection phase is also capable of folding multiple nodes into a single instruction. So here we have a floating point add and a load. And on x86, these can be selected into a single add SD. The R indicates that one of the operands is in register, and the M indicates that the other operand is in memory. You can notice that the add SD RM node has a lot more operands than the original add and load did. This is because instruction selection is also responsible for matching the addressing mode. So we'll actually climb up the tree of the selection DAG that produced the address and recognize adds and shifts and fold them into the addressing mode for the load. The select phase uses a sort of custom language for describing instructions that can be used to match nodes and transform them into machine-specific nodes. I selected this example from the PowerPC target because it's nice and simple. x86 is more complicated. So this is the basic description of an instruction, and there's lots of these. And there tends to be, in many instruction sets, a lot of redundancy. So we use a simple macro language. dform2 is a simple macro expansion for a common type of PowerPC instruction. And 14 is a parameter telling the code generator an opcode to use when this is being JITted. So we're actually going to be building up information about the binary encoding of the instruction with this. We also have operands indicating the output parameters and the input parameters. This is actually a string for the assembly printer. It will actually fill in the $ things, much like a printf will fill in format specifiers with individual registers and the actual immediate value. In this file, we can also have scheduling class information. So this is in the int general scheduling class. And then finally, we have a pattern to match. This is at the heart of how instruction selection works. Is it actually matches this sort of pseudo Lisp-like syntax with a tree in the DAG, and it will match it into this instruction. After we've selected the machine opcodes that we want to use, now we go into the schedule phase. At this point, we use a significantly simpler graph. At this point, we can cut out all the constant immediate values and all the basic block operands and measure the things that the scheduler doesn't need to worry about. The schedule graph, nodes in the schedule graph are called SUnits, and we actually explicitly track predecessors and successors in the scheduling graph. Those are called SDEPs for our scheduling dependencies. One of the interesting things that happens in the schedule graph is that our add carry and our add extended were actually folded into a single node here. This isn't strictly necessary on x86, but this is currently what we're using. It's a simple approach to make sure that the flag operand, the condition code, doesn't get clobbered by some other node getting scheduled in between the add with carry and the add extended. We also use a special technique to minimize the number of copies that are needed. So the x86 inc instruction is a read modify write, which clobbers its input. In order to avoid nodes that need to use that input requiring a copy to get the original value, we insert special dependencies into the scheduling graph to tell the scheduler, put every node that needs this input register above this inc so that they don't have to have a copy. In certain complicated situations, this can cause the scheduler to get in trouble. So the scheduler knows that those are special dependencies and they can be removed if it gets in trouble. Those are not required for correctness. They're just required as an optimization. So the scheduler's job is to do a topological sort in this graph. And I've shown a sample select schedule. And at the top, you can see that the schedule is not unique. There are multiple ways to schedule this graph correctly. And the decisions that the scheduler make can either be done to optimize for register pressure or to optimize for latency. Another thing that the scheduler has to worry about that's not obvious from the graph is physical register dependencies. So in this example here, there's a multiply node. On x86, the multiply instruction explicitly reads the EAX registers and the EDX register. And those are things that we can't easily represent in a dependency graph. So those are extra information that's not shown here that the scheduler has to keep in mind. The output of the scheduler is finally a linear sequence of instructions. Now we have the opcodes and we have the order that we want the opcodes in. The final task here is to fill in all the dependency edges with virtual registers, and the result is something that's ready to be handed off to registry allocation. So the SelectionDAG framework is capable of doing a lot of things. We're hoping to make it do a lot more things in the future. Coming very soon is a new legalized types infrastructure that's being worked on by Duncan Sands. What this is going to do is split the current legalize phase into two parts. We're going to legalize types, like the I64, separate from legalizing operations. For example, like a target that does not have an integer divide instruction, but has an alternate sequence that could be done. That's legalizing an operation. That will be split into a separate phase. We're also looking at extending the SelectionDAG framework to handle single entry, multiple exit regions. Currently, we can only handle single blocks at a time. We'd like to handle larger regions to get more optimal instruction selecting and better scheduling. And eventually, we're looking at having whole function SelectionDAGs. This will require a lot of scalability work because we're going to be representing a lot of data at the same time. We're hoping to do more precise dependencies. Right now, we have very conservative dependencies between loads and stores. This constricts scheduling, and we'd like to improve it using alias analysis and other techniques. We're also looking at how can we make this faster. In many use cases today, the SelectionDAG is the #1 compile time. If you look at the profile, SelectionDAG is way up at the top. So we're looking at how can we make it faster. And we're also thinking about sometime in the future, we may want to implement a Berg-style instruction selector. Berg is just a fancy algorithm for doing instruction selection. And the select phase is basically where we'd be thinking about implementing it. After SelectionDAG, CodeGen continues with some late code motion optimizations, registry allocation, which is a whole series of things that Evan will talk about, and then finally output for the machine code. So are there any questions? David.
Yeah, there's been some talk recently on the list about quote-unquote separating SelectionDAG or selection from scheduling. What does that mean, and what's it going to look like? Please repeat the question.
So the question is, there's been some talk about separating selection from scheduling, and I don't know what discussion offhand. I'm not.
There's been a few offhand comments on the mailing list about, oh, I'm working on this, or I'm not quite sure what that means.
Okay, I have to say that I don't know what that is. Yes, go ahead.
How good is the vector instruction selection, and are there plans to work on that in the future?
So the vector instruction selection is dependent on targets. Okay, so the question is, how good is the vector instruction selection? It's highly dependent on target, so PowerPC, AltaVec, x86 SSC, and each target has its own requirements for matching vector instructions, and they can vary with the target. For x86 SSC, we've put quite a lot of work into it, and it works fairly well. I understand that PowerPC also works fairly well. For an instruction set like MMX, for example, it doesn't get a lot of attention, so it doesn't work as well.
Any interprocedural or profile-guided optimizations?
Okay, the question is, are there any interprocedural or profile-guided optimizations? And the answer is no. We're not currently planning to do interprocedural code generation. The idea is if we're going to do interprocedural analyses, we'll do them up in the LLVM phase and do as much as we can there, and then have CodeGen just focus on doing an optimal job on a smaller scope. That's our current design idea. For profile-guided optimizations, we don't have it right now.
You mentioned you're actually working it below the function level. How is that carved out? How are you working? You say you're working on whole function, or you're going to be moving towards whole function?
Yeah, so currently we're just looking at one basic block at a time.
What's the basic
Okay,
block?
the question is, we're working on some sub-function regions of the program. A basic block is a region of code that has a single entry point and a single exit point. So if you have like an if statement, the body of the if statement will be a basic block, and then the code after the if statement will be another basic block, because you have two possible ways to get there.
And the optimizations, there's optimizations that are possible outside of that, or if you can
Yeah.
function that you,
So right now, the main LLVM phase, the main optimization phase, does a lot of optimizations that look across basic blocks. And the code generation phase is just focused on one basic block at a time. This works pretty well, but we think we can work even better if we can look at multiple basic blocks at a time in CodeGen.
So what
the plans for extending this to multiple basic blocks? When is it scheduled to?
Okay, the question is, what is the schedule for looking at multiple basic blocks? I don't think we have a formal schedule. I think what we have right now are some ideas, and some people have worked on some prototype work on it. But I'm not aware of any actual specific plans for scheduling.
In cases where register pressure is a concern, kind of scheduling, how does the scheduler switch modes to optimize for register pressure instead?
Okay, the question is, in cases where register pressure is concerned, how does the scheduler switch modes? And the answer is, right now, we don't switch modes in the middle. We just say, for x86, we're going to do set the element style scheduling, minimize register pressure, and that's it. That on x86, our primary concern is minimizing spillage and hopefully relying on the out-of-order machine to take care of the scheduling for us. Yeah, eventually, we're going to be looking at post-pass scheduling. That's something we'd like to look at. But we have a few steps we have to take before we can get to that point. David?
Actually, on the post-pass scheduling, is the intent to reuse some of this framework? Or what's...
Okay, the question is, for post-pass scheduling, is the intent to reuse some of this framework? And I think probably yes. I think that's beyond what anyone has actually concretely started thinking about yet. So specifically, before we can start doing post-pass scheduling, we have to resolve the dependency issues. We have to know loads and stores are pretty critical at that point.
You said basic blocks are single exit, so does that include instructions that can trap or throw exceptions? Are those considered endpoints?
So instructions that can throw exceptions in the object-oriented sense of throw exceptions, yes, that currently means that's terminating a basic block. For instructions that can trap, that's somewhat outside the compiler's concern. We need to preserve ordering for traps so that we don't put one trap above another trap, for example. But a trap basically means you exit to a signal handler, and that's not something that the compiler's control needs to worry about. Go ahead.
For embedded applications, what is the memory footprint of the selector right now? When you think about these pattern-based methods like Berg, do you expect it to increase or decrease?
Okay, the question is, what is the memory footprint of SelectionDAG? And as we go to Berg, is it going to increase or decrease? The memory footprint right now is I don't have numbers, I should say. We've recently done a lot of work to shrink the memory footprint. There's more work that we can do, certainly, to make it use less memory.
It's target dependent as well.
Yeah, it's also quite target dependent. As far as Berg goes, if and when we do Berg, it's almost certain that Berg would not be the only choice. That Berg would be a choice among other choices, and that different targets and different applications could make different choices. We already have a number of parameters in the code generation for disabling certain optimizations to make trade-offs for space and time and quality of generated code. So that would be likely one of those things. Any other questions? All right, thank you.